You are standing in a crater at the moon's south pole. The sun has not touched this floor for 2 billion years. The temperature is minus 240 degrees Celsius. There is no sound, no wind, no light, except the faint wash of stars and the blue-green crescent of Earth hanging low on the rim. You could walk across this regolith and leave prints that would last longer than the human species has existed. And just beneath your feet, a few meters down in the eternal dark, there is ice. Not a little. Enough to fuel a voyage to Mars. Enough to fill the tanks of rockets that have not yet been built. Russian detectors aboard an American spacecraft mapped that ice. And now the moon is not a grave. It is a port. Hello, and welcome to Penumbra. Tonight, the story of what Russia found at the moon's south pole, and why it changed the way we think about the future of human spaceflight. If you are new here, this is a channel for long, calm stories about the universe, made for sleep and for winding down. If that is what you came for, a subscribe genuinely helps, and I am always curious where you are listening from. Leave your location and the time in the comments. I read them. By the end of tonight, you will understand how a box of detectors, the weight of a large suitcase, built in a laboratory in Moscow and bolted to the side of an American orbiter, saw something no telescope and no camera could ever see. You will understand how it turned the moon from a dead endpoint of the Apollo era into a refueling station for the rest of the solar system. And there is one question that runs underneath the whole story. The question I want you to hold on to as we go: how could a small instrument, orbiting 100 kilometers up, detect water ice buried under a meter of rock in total darkness without ever seeing it? The answer is stranger than most people know. It begins with a mistake that lasted 30 years. The moon, for most of human history, was a dry bone. When the Apollo astronauts walked on the surface between 1969 and 1972, they brought back 382 kilograms of rock and soil. Every gram of it was catalogued, sealed, flown home, and studied in laboratories around the world for decades. The samples were volcanic basalts, dark and heavy, poured out as lava billions of years ago. They were breccias, jumbled rocks shattered and welded back together by the force of ancient impacts. There were tiny beads of orange and green glass, sprayed out of fire fountains when the young moon was still volcanically alive. Each sample told a story of a world that had melted, cooled, and been battered for 4 billion years. But one thing they did not contain was water. Not water in the crystals. Not water locked in the glass. Not water trapped as gas bubbles in the rock. The measurements came back again and again with the same answer: less than a few parts per billion of water in most samples. To a geologist, a number that small is not a little water. It is effectively zero. It is the signature of a world that had never had water, or had lost every trace of it long ago. There was even a subtle way in which the handling of the samples reinforced the dry conclusion. The lunar rocks were treated, understandably, as precious and fragile things sealed on the moon, opened on Earth inside cabinets flushed with dry nitrogen, kept away from the moist air of the laboratory precisely so that Earth's abundant water could not creep in and contaminate them. Everything about the care taken with the samples assumed there was no native water to protect, and that any water found must be a smudge of earthly contamination to be scrubbed away. When a trace of water did turn up in an analysis, the natural first assumption was that it had leaked in from the terrestrial environment, not that it belonged to the moon. The whole apparatus of caution was built around the certainty that the moon was dry, and that certainty quietly filtered how ambiguous results were read for decades. It would take instruments sensitive enough to see water locked deep inside sealed glass, where no earthly contamination could reach, to break the assumption open, but that was 30 years away. There was, beyond the samples, a good physical reason to expect exactly this. The leading explanation for the moon's origin, then as now, was the giant impact hypothesis. In the chaos of the early solar system, A body roughly the size of Mars struck the newborn Earth a glancing blow. The collision was so violent that it vaporized rock, flung a ring of molten and gaseous debris into orbit, and that debris eventually gathered itself into the moon. If that is how the moon was born, out of rock heated to thousands of degrees, boiled and flung into space, then any water, any volatile compound, anything that evaporates easily, should have been driven off entirely. Water would have boiled away into the vacuum before the moon ever solidified. A moon made this way would be born bone dry, and would stay that way. The samples seemed to confirm the theory, and the theory seemed to explain the samples. The circle was closed. Harrison Schmitt was the only professional geologist ever to walk on the moon. Every other Apollo astronaut was a test pilot first, trained in geology afterward. Schmitt was a scientist by training, and on Apollo 17, in December 1972, he was the man with the hammer and the practiced eye. Apollo 17 landed in the Taurus Littrow Valley, a deep notch between mountains at the edge of one of the moon's great impact basins, chosen precisely because a trained geologist could read more from that complex terrain than anyone had been able to read before. Schmitt collected a particular sample there, a titanium-rich basalt, dark and dense, that would later become a kind of touchstone for the whole idea of a dry moon. When it was analysed back on Earth, its water content sat down in the parts per billion range, the same near nothing as everything else. Schmitt would say, years later, that the lunar surface was among the driest material known to science. That became the textbook view, and it held for a generation. The moon had no water, no air, no life. It was a dead world, magnificent, silent, and finished. You could go there, you could plant a flag, gather rocks, and leave your footprints in the grey dust. But you could not stay, because there was nothing there to keep you alive. Everything a human being needs, every breath of oxygen, every mouthful of water, every gram of fuel to get home again, would have to be carried up from Earth at enormous cost. The moon was a place you visited and then abandoned, and for a while, that is exactly what humanity did. After 1972, no human being went back. There was, however, one detail in that dry picture that never quite fit, and it had been sitting in the scientific literature, ignored, since before Apollo ever launched. The Apollo samples came from the moon's equator. Every single landing, all 6 of them set down within a narrow band on the near side of the moon, close to the lunar equator, on flat, sunlit plains, chosen for the safety and simplicity of the landing. There were good engineering reasons for this. A landing near the equator is easier to reach, easier to communicate with, and gentler on the spacecraft. But it meant that the entire physical understanding of the moon, dry, dead, anhydrous, was built from samples of one kind of terrain, in one narrow band of latitude, in the warmest, most sunlit region of the whole world. No one had sampled the poles, no one had sampled the deep, cold shadows, and it was in the shadows. A small group of scientists had argued long before Apollo that the exception to the dry moon might be hiding. The samples were not wrong. The rocks Schmitt collected really were bone dry. The mistake was in assuming that the equator spoke for the entire moon. It did not. There was a part of the moon the astronauts had never touched, colder than anywhere they had ever imagined standing, and the rules there were different. It is a strange thing to sit with how a correct measurement, honestly made, can produce a wrong picture of the world simply because of where the measurement was taken. The Apollo scientists did nothing careless. They analysed real rocks with the best care of their era and reported exactly what they found. The rocks were dry. Their error, if it can even be called that, was one of reach. They had samples from a warm band around the middle of a world, and they let those samples speak for the whole of it, including places utterly unlike the ones they had visited. The moon they described was real. It was just not the entire moon. And the part they had missed, the cold, dark, shadowed part, happened to be the only part where the interesting thing was hiding. For 30 years, the map of the moon in every textbook was accurate and incomplete at the same time. and no one could tell the difference. Because to tell the difference, you would have had to go somewhere no one had been. The idea that ice could survive on the moon did not begin with Apollo. It began in 1961, 6 years before the Outer Space Treaty, 8 years before a human being set foot on the lunar surface, when 3 scientists at the California Institute of Technology sat down to think carefully about the coldest places on a world no one had yet visited. Their names were Kenneth Watson, Bruce Murray, and Harrison Brown. Bruce Murray would go on to direct the Jet Propulsion Laboratory, the place that would later build the robotic explorers of the outer solar system. Harrison Brown was a geochemist who had helped work out the composition of meteorites. But in 1961, the 3 of them were simply asking a physicist's question about a place they could only see through a telescope. If water molecules ever arrived at the moon, could any of them stay? At first glance, the answer is obviously no. The moon has almost no atmosphere. On the sunlit surface, temperatures climb well above the boiling point of water on Earth. Any ice exposed to that heat would sublimate, turn directly from solid to vapor, and the vapor, with nothing to hold it down, would drift off into space or be broken apart by sunlight. On the daylit moon, water has no future. It cannot last. But Watson, Murray, and Brown noticed something about the geometry of the poles. The moon's axis is barely tilted. Earth leans over by more than 23 degrees, which is why we have seasons the poles tip toward and away from the sun through the year. The moon leans by only about 1.5 degrees. It sits almost perfectly upright as it goes around, and that near-perfect upright posture has a strange consequence at the poles. There, the sun never climbs more than a degree or 2 above the horizon. It circles low, grazing the landscape, casting shadows that stretch for kilometers and never move. In that permanent low light, the deep floor of a polar crater, if the crater is deep enough, and its rim high enough, may never receive a single ray of direct sunlight. Not in a day, not in a year, not in a billion years. And a surface that the sun never touches, on an airless world, has no way to warm up. It just keeps radiating its heat away into the black sky, dropping colder and colder until it settles at a temperature only a few tens of degrees above absolute zero, the coldest temperature there is, the point at which molecular motion nearly stops. The 3 scientists worked out what that meant. If a water molecule wandering across the moon ever happened to fall into one of these permanently shadowed floors, it would freeze. And once frozen, at those temperatures, it would essentially never leave. The rate at which ice sublimates drops so steeply as temperature falls that, below about 100 Kelvin, a layer of ice could sit undisturbed for the entire age of the solar system, losing only a whisper of itself to space. The permanently shadowed crater would not just be cold, it would be a trap. Whatever fell in, stayed in. They called these places cold traps, and the name has stuck ever since. The theory was elegant and complete, but for one missing piece. Where would the water come from in the first place? The answer was all around the moon, in the traffic of the solar system. Comets are, in large part, dirty ice. They strike the moon from time to time, and each impact delivers a burst of water vapor. Water-rich asteroids do the same. Even the solar wind, the thin stream of particles blowing constantly off the sun, carries hydrogen that can combine with oxygen in the lunar soil to make trace amounts of water. Most of that water is lost. It lands in sunlight and boils away within hours. But a water molecule liberated on the surface does not simply vanish, and the way it moves is worth picturing. Because it is the mechanism that fills the traps. It hops, it absorbs a bit of sunlight, lifts off the surface in a long, slow, ballistic arc, and lands again somewhere else. And if that somewhere is still in sunlight, it lifts off once more. Each hop is short-lived and dangerous for the molecule. In sunlight, it can be broken apart by ultraviolet radiation or knocked away into space entirely. Any given molecule is far more likely to be destroyed than to survive. But there are so many molecules, and the process runs for so long, that even a tiny surviving fraction adds up. Molecule by molecule, hop by random hop, a small share of all that water performs, a slow migration across the surface, a random walk, drifting on average toward wherever it is coldest, because a molecule that lands somewhere cold hops less often and so lingers longer, and the coldest places of all are the polar shadows. A molecule that finally lands inside a permanently shadowed floor stops hopping altogether. There is no sunlight there to lift it off again. It freezes to the ground and stays. The cold trap is a one-way door. Water can wander in, but it cannot wander back out. Over billions of years, molecule by patient molecule, the traps fill. What waits in the shadows today is the accumulated residue of every watery thing that has struck or grazed the moon since the traps first went cold. A slow sediment of the solar system's water gathered a molecule at a time. Nearly 2 decades later, in 1979, a scientist named James Arnold took the idea further. Arnold built a more detailed model of exactly how water would migrate to the lunar poles and how much might accumulate, accounting for the various sources, the losses to sunlight and space, and the efficiency of the traps. His conclusion was that the poles could hold a genuinely significant quantity of water ice, buried and preserved perhaps billions of tons, spread thin through the polar soil over the age of the moon. The theory now had numbers attached to it. It predicted a resource, and yet it remained, for another 2 decades after that, exactly what it had always been, a theory, an elegant argument on paper describing a place no instrument had ever examined. The cold traps were real, the physics of the poles guaranteed that the shadows existed and that they were cold, but whether anything was actually inside them, whether the traps had truly filled over the aeons or sat empty, no one could say. You could not see into a permanently shadowed crater. That was the whole point of it. It was, by definition, a place where no light ever fell, and a camera, however good, can only photograph what light reveals. To look inside the darkest places on the moon, someone would need a way of seeing that did not depend on light at all. Before we get to the instrument that finally looked inside, it is worth standing for a moment at the place itself, because the south pole of the moon is unlike anywhere the astronauts ever saw, and unlike anywhere on Earth. Picture the terrain the Apollo crews walked. Flat grey plains, rolling gently to a close horizon, lit by a sun high overhead, with shadows short and sharp beneath the rocks. That is the equatorial moon. Now travel south, past the middle latitudes, toward the bottom of the world. The ground grows rougher. You are entering the outer edge of one of the largest impact scars in the solar system, a vast, ancient basin gouged out billions of years ago by a collision so enormous it left a depression thousands of kilometers wide, and, in places, deeper than any canyon on Earth. The rim of that basin and the countless craters piled on top of it make the South Polar region a chaos of ridges, peaks, and pits. And over all of it, the sun hangs low. It does not rise and set the way it does at the equator. It slides around the horizon, endlessly, barely clearing the tops of the ridges. Stand on a high point and the sunlight, coming in almost flat, throws your shadow out for hundreds of meters. Step down into a hollow, and the ridge behind you may block the sun entirely, and if the geometry is right, block it forever. This produces 2 kinds of extraordinary place, sitting side by side. On the high ground, the tops of certain crater rims and ridges, the sun almost never sets. As it circles the horizon, it stays above these peaks for the great majority of the lunar year. Astronomers of the 19th century, imagining the lunar poles long before anyone could go there, gave these places a name that has never been improved upon: the peaks of eternal light. On a world where the day and night each last 2 weeks, a place bathed in near-continuous sunlight is a treasure. It means near-constant solar power. It means moderate, stable temperatures instead of the brutal swing between lunar noon and lunar midnight. If you were going to build a base at the South Pole, you would build it on a peak of eternal light. And then, sometimes only a few hundred meters away and a few hundred meters down, is the opposite kind of place, the permanently shadowed floor. Here the numbers stop feeling real. The diviner instrument, an infrared radiometer flown on the American orbiter we will come to shortly, measured the surface temperatures inside these shadows directly. In the coldest of them, the thermometer read down around 25 to 30 Kelvin, 25 to 30 degrees above absolute zero. That is colder than the surface of Pluto, 4 billion kilometers farther from the Sunday. These permanently shadowed crater floors are among the coldest places that have ever been measured anywhere in the solar system. Not because they are far from the sun, they are the same distance as we are, but simply because the sun's light has never once reached them. Stand, for a moment, on one of those high sunlit rims. The sun sits on the horizon, low and unmoving, and it will stay there. It does not climb, it does not set. It only slides slowly sideways along the skyline as the weeks pass. Your shadow stretches away from you across the grey ground, impossibly long, a thin dark line reaching hundreds of meters toward the crater below. The earth hangs in the black sky, a small blue and white marble, fixed in place, never rising and never setting, because the same face of the moon has always looked toward home, and directly below you, a few hundred meters down the slope, is the edge of a shadow that has not moved in 2 billion years. Take a few steps down toward it. The temperature under your feet, if you could feel it, would be falling faster than anywhere on Earth, from the warmth of standing sunlight toward a cold near the very bottom of the temperature scale. Cross the shadow line, and you would step out of the longest day in the solar system and into the longest night in a single stride. There is no dawn on that floor, and there never has been. That is the ground the whole story is about. The contrast, over a short walk, is almost violent. A sunlit ridge at the pole can sit at temperatures well above the boiling point of water. A shadowed floor a short distance below can sit near absolute zero. Nowhere else in the solar system does the temperature swing so wildly across such a small distance and stay that way permanently. The poles of the moon are a place of thresholds cross one ridgeline, and you cross from one of the hottest environments to one of the coldest. And there is no gentle transition between them, only the hard, straight edge of a shadow that has not moved in 2 billion years. If the cold trap theory was right, those shadowed floors were the vaults. And if the vaults held ice, then the value of that ice, to anyone hoping to travel beyond the Earth, was almost impossible to overstate. Water is not just for drinking, though of course it is that too. Water, on a world with sunlight and the right equipment, is fuel. Run an electric current through it, and it splits into hydrogen and oxygen, the hydrogen a rocket fuel, the oxygen both the thing you burn it with and the thing you breathe. A world with water is a world you can live on and launch from. A world without it is a place you visit and flee. The economics of this are stark, and they turn on a single brutal fact about leaving Earth. Every kilogram you launch from the surface of our planet has to be dragged up out of Earth's gravity, and the cost of doing so is enormous. To deliver a single kilogram of anything all the way to the surface of the moon costs, by most estimates, somewhere in the range of hundreds of thousands of dollars. A litre of water weighs 1 kilogram, so a single litre of drinking water carried from Earth to the moon costs more than a new car. A modest tankful would cost more than a house. Carry everything a lunar base needs from Earth, and the base is impossible. You would spend a fortune just to keep a handful of people alive for a handful of weeks. But if the water is already there, frozen in the shadows, the arithmetic inverts. You do not carry the water, you carry the machine that digs it out. You arrive at the moon with your tanks half empty, fill them from the ground beneath you, and leave again for Mars, for the asteroids, for the moons of Jupiter, without ever having paid to lift that fuel off the Earth. The moon stops being a destination at the end of a very expensive road. It becomes a filling station on the way to everywhere else. That was the prize hidden in the shadows, not just water, but a different shape for the whole future of spaceflight. All that stood between the theory and the prize was proof, and proof for 4 decades was the one thing no one could get. You cannot photograph the inside of a permanently shadowed crater because there is no light to photograph it by. Radar can bounce a signal into the dark and read the echo, and in the 1990s, a small mission called Clementine, a joint project of the American Defense Department and NASA, tried exactly that. Clementine was, in its origins, as much a military test as a science mission, a chance to fly a set of lightweight sensors designed with defense work in mind out to the moon and see how they performed. But its scientists seized the opportunity, and among the experiments they ran was a clever one. They used the spacecraft's radio transmitter to send a signal down into the south polar shadows and listened, with antennas back on Earth, for the faint echo that bounced back. The character of that echo can, in principle, betray the presence of ice, because ice reflects radio waves differently than rock does. The result hinted at ice, but only hinted. The echo it returned was ambiguous. It could have come from buried ice. It could just as easily have come from rough, blocky, jumbled ground, which can mimic the same signature. For years afterward, scientists argued over which it was, and the argument was never fully settled. Radar had knocked on the door of the shadows and gotten a muffled, uncertain answer through it. A single hint, hotly disputed, was all anyone had, and it was not enough to build a future on. What was needed was a way to see not the surface of the dark, but into it through a meter of pulverized rock, and to count, specifically, the atoms of hydrogen hiding there, because hydrogen is the fingerprint of water. And the astonishing thing is that the moon itself provides exactly the light needed to do this. Not visible light, a different kind, one that shines out of the ground everywhere on the moon, all the time, and that most people have never heard of. The story starts with cosmic rays. These are not rays in the ordinary sense, they are particles, mostly the bare nuclei of atoms, protons and heavier fragments, hurled across the galaxy at nearly the speed of light. They come from the shockwaves of exploded stars, from the whirling magnetic fields of neutron stars, from the violent cores of distant galaxies. They fill the galaxy, and they rain down on every unshielded surface, including the surface of the moon, without pause. Earth is protected from most of them by its thick atmosphere and its magnetic field. The moon has neither. On the moon, the cosmic rays strike the bare ground directly, and when a cosmic ray, a proton moving at a good fraction of the speed of light, slams into the nucleus of an atom in the lunar soil, into a nucleus of silicon or oxygen or iron, it shatters it. The collision is so energetic that it blows the nucleus apart, and among the fragments that spray out are neutrons, free neutrons, particles that normally live locked inside atomic nuclei, now flung loose and travelling fast. Each cosmic ray strike liberates a spray of these fast neutrons into the soil. Those neutrons do not escape immediately. They ricochet through the regolith, colliding with one nucleus after another, and with each collision they lose a little energy and slow down. Physicists have names for the stages of this slowing. Fresh from the impact, they are fast neutrons. After some collisions, they slow to an intermediate range called epithermal. Slower still, and they become thermal neutrons, drifting at the speed set by the temperature of the soil. And at every stage, some of them work their way back up to the surface and leak out into space. The result is that the entire moon glows, faintly and invisibly, with a steady drizzle of neutrons streaming up from its surface. You cannot see this glow, but an instrument built to count neutrons can, and it turns out that the glow carries a message about what is buried in the ground. Before we get to how the neutrons reveal water, it is worth asking where the water inside the moon's soil comes from at all, because there is more than one source, and they matter differently. The most obvious is impact comets and water-rich asteroids striking the moon across billions of years. each one delivering a burst of water that, mostly, is lost to sunlight and space, but a fraction of which migrates to the cold traps and stays. That is the dramatic source, the one that fills the deep polar reservoirs. But there is a second, quieter source that works everywhere on the moon, all the time, and it is stranger. The solar wind, the thin, endless stream of particles blowing off the sun, is largely made of protons, which are simply the nuclei of hydrogen atoms. Those protons slam into the lunar soil across the entire sunlit surface and bury themselves in the grains. And there, some of them bond with oxygen atoms already locked in the minerals, forming water and its close chemical cousin, hydroxyl. Molecule by molecule, the moon, in other words, is slowly manufacturing a thin film of water across its whole face, out of hydrogen handed to it by the sunday. Most of that surface water is faint, bound tightly into grains, and useless as a resource. But it is there, and it is part of why a neutron detector sees hydrogen almost everywhere, and why the truly rich deposits, the ones worth crossing space for, are only the ones the cold traps have concentrated over the eons. The message the neutrons carry is hidden in a simple piece of physics, and it comes down to a coincidence of mass. A neutron weighs almost exactly the same as a proton, and the nucleus of a hydrogen atom is nothing but a single proton. So when a moving neutron happens to strike a hydrogen nucleus, it is striking something of nearly its own mass, and that fact governs how the collision unfolds. Think of a billiard ball striking another billiard ball head-on. The first ball can stop almost dead, handing nearly all of its motion to the second. That is what a neutron does when it hits hydrogen. In a direct hit, it can lose almost all of its energy in a single bounce, and even in glancing hits it loses a large share. Hydrogen is uniquely good at slowing neutrons down. It is, in the language of reactor physics, the best moderator there is. Now compare that to a neutron striking a heavy nucleus. Oxygen, say, or silicon, or iron. That is like a billiard ball striking a bowling ball. The billiard ball bounces off and keeps almost all of its speed. The heavy ball barely moves. A neutron hitting a heavy nucleus loses only a tiny fraction of its energy. So if the lunar soil in some region contains even a small amount of hydrogen, the neutrons passing through it get slowed far more efficiently than they would in ordinary rock. Fewer of them make it back to the surface, still traveling at epithermal speeds, because the hydrogen has knocked so many of them down into the slower thermal range. From orbit, a region rich in hydrogen shows up as a dip, a deficit in the count of epithermal neutrons streaming out of the ground. That deficit is the signature. Fewer epithermal neutrons over a patch of the moon means hydrogen is buried there. The method cannot, by itself, tell you what molecule the hydrogen belongs to. It might be water ice. It might be hydroxyl bound into minerals. It might be methane or ammonia, or it might be lone hydrogen atoms implanted by the solar wind. But it tells you, unambiguously, that hydrogen is present, and roughly how much. And if the hydrogen shows up precisely where the cold traps are, in the permanently shadowed, ultra-cold floors, then water ice becomes the natural, almost inescapable explanation, because those are exactly the places the cold trap theory says water should collect. It is worth stopping to appreciate how strange this way of seeing really is. Everything else in the history of exploration has come down, ultimately, to light, to reflected sunlight caught by an eye, or a lens, or a photographic plate, to the glow of things hot enough to shine. To map a coastline, you photograph it. To study a distant galaxy, you gather its light. But here is a method that does not use light at all. It waits for particles born of exploded stars on the far side of the galaxy to strike the moon and knock neutrons loose from its soil. It watches those neutrons slow as they pass through hidden hydrogen, and from the faint deficit in the neutrons that leak back out into space, it deduces the presence of water buried in permanent darkness, a meter underground, in a place where no light has fallen for 2 billion years, and no camera could ever record a thing. The chain of physics that connects a dying star to a puddle of ice in a lunar crater is long and improbable, and a small box in orbit reads the whole chain backward to reach the ice. There is nothing quite like it in the rest of science. It is seeing without light, in the truest sense. The scientist who first brought this technique to the moon was William Boynton, a planetary scientist at the University of Arizona. Boynton had spent his career on the physics of using natural radiation to read the composition of planetary surfaces. He had built a gamma-ray spectrometer for the Mars Observer mission, a spacecraft that was lost in 1993, just before it reached Mars, a hard loss, years of work gone silent, but the expertise remained. So when NASA approved the low-cost mission called Lunar Prospector to orbit the moon, at the end of the 1990s, Boynton proposed flying a neutron spectrometer, an instrument tuned to count exactly those telltale neutrons in their 3 energy bands. Lunar Prospector was a modest spacecraft, a drum-shaped little probe led by a scientist named Alan Binder, flown on a shoestring budget compared to the great flagship missions. It carried, among other things, the ashes of the geologist Eugene Shoemaker, one of the founders of the science of impact craters, who had always wanted to go to the moon and never had the chance in life. It launched in January 1998 and settled into a low polar orbit, circling the moon from pole to pole while the moon turned beneath it, so that over time the instrument swept across the entire surface. Almost immediately, the neutron data showed something. Over both poles, north and south, the count of epithermal neutrons dipped. Hydrogen was there, concentrated toward the poles, exactly where the cold trap theory had predicted for nearly 40 years. Boynton's team estimated that, if the hydrogen were in the form of water ice, the poles might hold the equivalent of several 100 million tons of it. In March 1998, the finding was announced, and for the first time the phrase "water on the moon" appeared in headlines not as speculation but as a scientific result. After decades of theory, an instrument had finally caught the signal, but there was a catch, and it was a serious one. Lunar Prospector's neutron spectrometer had no way to focus its view. It simply counted every neutron arriving from the whole face of the moon spread out beneath it. From its orbital altitude, the patch of surface it was effectively averaging over was something like 150 kilometers across, wider than many of the craters it was flying over. So when Boynton saw a hydrogen signal near the South Pole, he could not tell where within that huge blurry patch the hydrogen actually sat. Was it concentrated down inside the permanently shadowed crater floors as water ice, exactly where the theory said, or was it spread thinly across the sunlit polar plains in the form of hydrogen implanted by the solar wind, of no use to anyone? The instrument could not distinguish the two, and the difference between them was the difference between a treasure and a mirage, between a resource you could mine and a diffuse haze of atoms you could never gather. Boynton knew this, and said so plainly. In his papers he wrote that the signal was consistent with water ice, but that other explanations could not be ruled out. The data had opened a door. They could not walk through it. The view was simply too blurred. It is worth dwelling on how much rode on that blur, because it is easy, knowing how the story ends, to underrate the doubt. If the polar hydrogen was thin, solar wind hydrogen spread across sunlit ground, then the whole dream of a lunar filling station was a fantasy you cannot mine, a haze of atoms too dilute and too scattered to gather. If, instead, it was concentrated water ice down inside the cold traps, then everything became possible. Those two futures looked identical to Lunar Prospector's blurred eye. The instrument could tell you there was hydrogen near the poles, and it could tell you roughly how much, but on the one question that decided whether the moon had a future as a place to live and launch from, it had to shrug. For over a decade, that shrug stood. The most important fact about the moon's usefulness to humankind was known to be almost certainly one thing, and almost certain was not good enough to build a spacecraft around. Someone had to make the picture sharp. There was even an attempt to force the question, and it foreshadowed everything that would come a decade later. When Lunar Prospector reached the end of its mission, in July 1999, its controllers decided to use the dying spacecraft as a projectile. They aimed it at a permanently shadowed crater near the South Pole and crashed it deliberately into the dark, hoping the impact would blast up a plume of debris and that if there was ice down there, a puff of water vapor might rise high enough to be caught by telescopes back on Earth. Astronomers watched and waited. Nothing was seen. No plume, no water, no signal of any kind. It proved little. The spacecraft was small, the aim uncertain, the crater vast, but it was a first, crude attempt to hit the shadows and read what came out. It would not be the last. First, though, someone had to solve the blur. To go from a blurred hydrogen smear to a sharp map of individual craters, you would have to narrow the instrument's field of view by a factor of 10 or more to build a neutron spectrometer that ignored almost the entire moon and looked only at a small patch directly beneath the spacecraft. And that is a genuinely hard thing to do, because neutrons cannot be focused. Light can be bent by a lens or bounced off a mirror, because light is an electromagnetic wave, and glass and metal push on it. A neutron carries no electric charge. It ignores lenses, ignores mirrors, sails straight through magnetic fields as if they were not there. There is only one way to control where your neutrons come from. You have to absorb the ones you do not want. You have to wrap your detector in a thick shield that swallows every neutron arriving from the sides, leaving only a narrow hole at the bottom through which neutrons from the patch directly below can enter. That kind of shield is heavy, it is bulky, and before this story it had never been flown to another world. The person who set out to build it worked not in America, but in Moscow, at an institution called the Space Research Institute, known by its initials in Russian, and referred to here simply as the Institute. His name was Igor Mitrofanov, and he was the head of its laboratory for gamma-ray and neutron spectroscopy. He was not a newcomer to the problem of finding hidden water on other worlds. He had, in fact, already done it once on Mars. In the late 1990s, Mitrofanov's team had built an instrument for an American mission to Mars called Mars Odyssey. The instrument was a neutron detector, the same basic physics. Cosmic rays making neutrons, hydrogen slowing them down, and its job was to search the Martian soil for buried hydrogen. Mars Odyssey reached Mars in 2001, and within months the Russian detector delivered one of the great results in the history of planetary science. The signal was overwhelming, not a subtle dip like the one that would later hide in the lunar data, but a huge, unmistakable suppression of neutrons across vast regions near the Martian poles, so strong it could only mean one thing. Enormous quantities of hydrogen, interpreted as water ice, were frozen into the Martian soil, so much of it in places that the upper meter of ground had to be more ice than rock. The permafrost was not a curiosity in a few sheltered spots. It stretched across continent-sized swaths of the planet, buried just beneath a thin, dry skin of dust. Mars, it turned out, had buried permafrost on a continental scale. The announcement, in 2002, reshaped the understanding of Mars from a bone-dry desert into a world with immense reserves of frozen water hidden just beneath the surface. It is not too much to say that this single instrument helped set the direction of Mars exploration for the next 20 years. It is worth pausing on the kind of place this instrument came from, because it shapes the story. The institute in Moscow, where Mitrofanov worked, was a child of the old Soviet space effort, the same intellectual lineage that had sent the first probes to Venus and Mars and built the first machines to land on the moon. By the time Mitrofanov was leading its neutron and gamma-ray work, that lineage had passed through the collapse of the Soviet Union, through years of desperate underfunding, when Russian space science survived on almost nothing, kept alive by scientists who stayed at their benches for salaries that barely paid. What the Institute had, that money could not buy, was expertise, a deep, unbroken tradition in exactly the kind of nuclear and particle instrumentation that neutron spectroscopy demands. Mitrofanov himself was a physicist of the old school, more interested in the physics of the measurement than in the spectacle around it. The sort of scientist who would rather spend an hour on the design of a shield than a minute in front of a camera. And he had made a career, unusually, by putting Russian instruments aboard the spacecraft of other nations on American missions, and later European ones, in an era when Russia's own planetary program had all but stopped flying. If Russia could not send its own probes to Mars and the Moon, its scientists could still ride along on everyone else's and see with their own instruments. That was the quiet strategy behind the neutron detector, and it is why the definitive map of American and international lunar ambitions would end up being drawn, of all places, in Moscow. That success taught Mitrofanov two things. The first was that neutron spectroscopy worked, that you really could sit in orbit and map the water hidden in the ground of another planet. The second was subtler and more important. The Mars detector had carried a modest collimator, a partial shield that narrowed its view enough to resolve large geological regions. It was that focusing, crude as it was, that turned a vague global signal into a usable map. Mitrofanov understood, better than almost anyone, that the whole game came down to the field of view. Sharpen the view, and you turn a smear into an atlas. And he saw that if he could build a far more aggressive collimator, a much tighter shield, a much narrower hole, and fly it to the Moon, he could finally answer the question that had defeated Lunar Prospector. He could point it at the shadows and see, crater by crater, whether the hydrogen was really down inside the dark. The engineering was formidable. To stop neutrons, you need materials that greedily absorb them, and one of the best is a form of boron, an isotope that captures slow neutrons and instantly splits apart, swallowing them for good. Mitrofanov's team surrounded their neutron detectors with a thick jacket of boron-loaded plastic and dense metal, shaped so that the only path a neutron could take into the detectors was straight up through a narrow opening at the base. Neutrons coming from the sides ran into the jacket and were absorbed. Only neutrons from the small patch of ground directly below could reach the sensors. The detectors themselves were tubes filled with helium-3 gas, a rare and precious form of helium so scarce, in fact, that it is one of the resources people sometimes imagine one day mining from the Moon itself. When a neutron enters such a tube and strikes a helium-3 nucleus, it triggers a tiny nuclear reaction, splitting into two charged fragments that tear through the gas and leave a faint trail of electrical charge, which the instrument reads as a single clean pulse. Each pulse is one neutron caught. There is an elegance to the whole scheme that is easy to miss. The instrument has no lens, no shutter, no image at all. It simply sits in the dark and counts particles, one at a time. And from nothing but a rising and falling tally of counts as it flies over the surface, it reconstructs a map of water hidden underground. It is a way of seeing that owes nothing to light. The physics of why this is so hard bears repeating, because it is the crux of the whole instrument. With light, you focus by bending. A curved piece of glass gathers rays spreading from a point and brings them back to a point. And that is why a camera can take a sharp picture. It collects light from a wide area and sorts it, ray by ray, onto the right place. None of that is available for neutrons. A neutron carries no electric charge, so electric and magnetic fields, which steer charged particles beautifully, have no grip on it at all. It will not bend around a curve or bounce off a mirror in any useful way. The only handle you have on a neutron is destruction. You can let it through, or you can absorb it, and that is all. So to build a sharp view, you cannot gather the neutrons you want, you can only throw away the ones you do not. You surround your detector with a thick wall of absorbing material and leave a single narrow window at the bottom, and you accept that every neutron arriving from any direction but straight down will simply be swallowed by the wall and lost. It is focusing by subtraction, by discarding almost everything, keeping only the thin pencil of neutrons rising from the patch directly below. That is a wasteful, brute way to make a picture, and it is the only way there is. Every part of this was a compromise between competing demands. More shielding meant a sharper view, but more mass, and mass on a spacecraft is fought over gram by gram, because every gram costs fuel to launch. A narrower opening meant sharper resolution but fewer neutrons getting through, and fewer neutrons meant a fainter signal that took longer to build into a reliable measurement. The whole thing had to survive the shaking of launch, the swing between blazing sunlight and deep cold in orbit, and years of operation with no one to repair it. Mitrofanov's team worked through dozens of designs, testing them with neutron sources in the laboratory and simulating their behavior on computers, hunting for the geometry that gave the best possible view for the least possible weight. The instrument they built was named the Lunar Exploration Neutron Detector. In this story, it will simply be the detector or the neutron detector, and when a short name is needed, its makers called it by the acronym that reads, aptly enough, as the word lend, as if the moon were only lending its secrets to whoever built the right tool. It weighed around 26 kilograms, drew about as much power as a household light bulb, and held two kinds of sensor inside its shielding. One set looked at the whole moon below, without collimation, the way Lunar Prospector had a fallback, a way to reproduce the older global measurement with better precision. The other set, the collimated sensor, was the heart of the whole idea. Through its narrow, shielded aperture, from the planned orbit 50 kilometers up, it would see a patch of the surface only about 10 kilometers across. 10 kilometers. That was the number that mattered, because 10 kilometers was roughly the size of the larger, permanently shadowed craters. For the first time, an instrument would be able to look at the hydrogen inside a single shadowed crater floor and compare it directly with the sunlit ground just outside and see whether they differed. But building the instrument was only half the problem. The other half was getting it flown, and that ran straight into politics. The detector was Russian. The mission that would carry it, the Lunar Reconnaissance Orbiter, was American, a flagship of NASA's return to the moon, and the early 2000s were not a warm moment between the two nations. The bright optimism of the 1990s, when American shuttles docked with the Russian space station Mir and the two countries began building the International Space Station together, was cooling into friction over missile defense, over the expansion of NATO, over the wars of the decade. The idea of bolting a Russian scientific payload onto the side of a flagship American moon mission made some people inside NASA distinctly uncomfortable. Mitrofanov had an advocate on the American side, Alan Stern, a planetary scientist who would later lead NASA's entire science program, believed both in the instrument and in the principle of working across the divide. Stern's argument was practical. The United States did not have a collimated neutron spectrometer ready to fly to the moon. The Russian team did. They had the design. They had the flight experience from Mars. They had an instrument essentially ready to build. It was light. It was cheap. Offered at no cost to NASA, it would give the American mission a unique capability that nothing in the existing plans could match. To Stern, turning it down for the sake of an all-American payload list would be throwing away a decisive scientific tool out of pride. Not everyone agreed. Some NASA engineers preferred a fully domestic instrument suite, and they had real reasons a foreign payload meant different electrical standards, different data formats, different testing regimes. All of it added risk to a complex mission, and some scientists raised a sharper, more technical worry, one that would echo for years afterward. Would the collimation actually work? The physics was sound in principle, but no one had ever flown so aggressive a neutron shield in lunar orbit. What if neutrons scattered off the shielding and leaked into the detectors from the wrong directions, blurring the sharp view the whole design depended on? What if the narrow aperture let through so few neutrons that the signal drowned in noise? These were legitimate questions, and they were argued out in review after review through the middle of the decade. In the end, the two space agencies signed a formal agreement. Russia's space agency would provide the neutron detector as a contributed payload at no cost and deliver it for integration into the American orbiter. NASA would operate it and share all of its data with the Russian team. It was a bargain struck across a widening political gulf, a quiet statement that lunar science, at least, could remain a place where the two old rivals still built something together. It is worth sitting with how unlikely that agreement was, and how much it depended on individual people choosing cooperation over suspicion. This was not a warm partnership between allies. It was two rival powers, with a long history of mutual distrust and a present full of friction, agreeing to bolt one nation's most sophisticated scientific instrument onto the other nation's flagship spacecraft, share its data completely, and trust that the arrangement would hold across whatever political storms came. It held because a handful of scientists and administrators on both sides decided that the science was worth more than the rivalry, that the question of whether there was water on the moon was a human question, not an American or a Russian one, and that the fastest way to answer it ran straight through the divide. In the years that followed, relations between the two nations would sour badly, and much of their cooperation in space would come under strain. But the neutron detector kept flying, and kept counting, and kept handing its data to everyone, a small artifact of a moment when the two powers chose, on this one narrow matter, to work together. There is something quietly stubborn about that. The instrument did not care about the politics that surrounded its birth. It simply did its job. Mitrofanov's team spent 3 years constructing and testing the instrument, and by 2008 it was finished, shipped across the world, and bolted onto the flank of the spacecraft that would carry it to the moon. Everything now depended on whether, once it was up there in the dark, the sharp view would hold or dissolve into the same blur that had defeated everyone before. On the 18th of June, 2009, an Atlas rocket lifted off from Cape Canaveral carrying 2 spacecraft toward the moon. The larger was the Lunar Reconnaissance Orbiter, the flagship, loaded with 7 instruments meant to map the moon in more detail than anyone ever had its shape, its temperature, its radiation, its shadows, and its hidden hydrogen. The smaller, riding along on the same rocket, was an impactor mission we will come to shortly. For now, follow the orbiter. The launch was the smooth, kind of uneventful that engineers pray for. The orbiter separated cleanly and began a 4-day cruise across the 250,000 kilometers to the moon. During those days, the instruments were switched on and checked, one by one. The neutron detector powered up. Its sensors began to register the thin trickle of neutrons that fills deep space, not many, because far from any large body the neutron background is low, but enough to prove the electronics were alive and counting. In Moscow, Mitrofanov and his team watched the numbers arrive through a relay from the Mission Control Center. Their instrument, 3 years in the building, was working. The orbiter reached the moon on the 23rd of June and slipped into orbit, and over the following weeks its controllers gradually lowered and circularized its path until it was flying a tight loop from pole to pole, only 50 kilometers above the surface, sweeping over each pole roughly every 2 hours as the moon rotated slowly beneath it. From that low, fast orbit, the collimated neutron sensor would trace a narrow line across the ground on every pass, a strip only a few kilometers wide, laying down its measurements, track by track like a plow, turning a field one furrow at a time. The neutron detector did not fly alone, and the other instruments on the orbiter deserve a word, because several of them were quietly attacking the same darkness by completely different means. The infrared radiometer read the surface temperatures, and it was this instrument that measured the record-breaking cold inside the shadows. The readings, near 30 Kelvin, that made the permanently shadowed floors the coldest measured places in the solar system. The laser altimeter fired its pulses to map the exact shape of the land, and in doing so it also read how brightly its own laser light reflected back and found, in some shadowed floors, patches unusually bright, exactly as one would expect if frost were mixed into the surface soil. And there was a third instrument, an ultraviolet spectrograph, that used one of the most beautiful tricks in the whole mission. It could not carry its own lamp to shine into the dark, so it used the only light available, The faint ultraviolet glow of the sky itself, the diffuse shine of distant stars, and the thin hydrogen haze that fills the space around the Sunday. That whisper of ultraviolet light falls even into the permanently shadowed craters, far too dim for a human eye, but enough for a sensitive detector to read the surface it lands on. Using nothing but starlight, that instrument, too, found the ultraviolet signature of water frost dusting the shadowed floors. 3 instruments, working by heat, by laser, and by starlight, all converging on the same conclusion the neutrons were building toward. The moon was being caught out from several directions at once. Before the polar hunt could begin, the neutron instrument had to be calibrated, its readings checked against known, ordinary terrain. So in the first weeks, the team measured the neutron glow over the familiar equatorial plains, the dark volcanic seas and the bright ancient highlands, building a baseline for what normal, dry lunar ground looked like. The uncollimated sensor quickly reproduced what Lunar Prospector had found a decade before. The broad rise in polar hydrogen, the same blurred signal, now measured with a steadier hand. That was reassurance, not revelation. It confirmed the instrument agreed with the past, but the whole reason for its existence, the collimated sensor with its narrow shielded eye, had not yet been turned loose on the shadows. That was about to change. Mitrofanov worked from an office at the Institute in Moscow, a room stacked with papers and dominated by a large monitor, and it was there that the first sharp data from the South Pole began to arrive. There was no single instant of revelation, no image snapping suddenly into focus the way a telescope resolves a new world. It came slowly, and it had to. The collimated sensor, seeing only its narrow patch, caught just a few neutrons every second, a thin trickle of counts. To build a map, you had to gather those counts over many, many orbits, laying track beside track, binning them into pixels on the surface, correcting for the spacecraft's exact height and orientation, for the ever-shifting cosmic ray background, for the moments the detector was busy and could not count. The picture accumulated the way a photograph develops in a tray of chemicals, nothing, then a ghost of something, then, gradually, detail. There is a particular kind of patience this work demands, and a particular kind of doubt that comes with it. When the signal you are hunting for is a small dip in a faint trickle of counts, buried under a fluctuating background, you cannot trust any single track. A dip in one pass might be real, or it might be noise, the random flicker of too few neutrons counted over too little time. Only when the same dip appears again and again, over dozens of passes across the same ground, does it climb out of the noise and become a fact. So the work is a long argument with yourself. Is that a real feature, or am I fooling myself? You add more data. You watch the faint pattern either firm up into something solid or dissolve back into randomness. It is the opposite of a sudden discovery. It is a slow settling of confidence over months as the noise averages away and the truth, if there is one, refuses to leave. And as the tracks piled up, a pattern began to surface. Here and there, as the narrow sensor crossed certain patches of high-latitude ground, the epithermal neutron count dipped. At first, the dips were faint and scattered, but with more orbits they sharpened and steadied, and they were not spread evenly across the pole. They were clustered, patchy, local. Some areas showed a clear deficit. Others, right beside them, showed nothing at all. The decisive moment came when the team laid their map of neutron dips over a different map entirely, a map of shadow. Another instrument on the same orbiter, a laser altimeter, had been firing pulses at the surface and timing their return to build an exact model of the lunar terrain, ridge by ridge and crater by crater. From that precise shape of the land and the known path of the sun, you could calculate exactly which patches of ground never, ever received sunlight. You could draw the outlines of the permanently shadowed regions with confidence. When Mitrofanov's team overlaid their hydrogen map onto that map of eternal shadow, they saw the thing they had built the instrument to see. Every significant dip in the neutrons fell inside a permanently shadowed region. Not most of them. Every one. The patches where hydrogen hid, and the patches the sun had abandoned billions of years ago, were the same patches. Crater by crater, the dark floors and the buried hydrogen lined up, one to one, as closely as the instrument could measure. Where the shadow was, the hydrogen was. Where the sunlight fell, even on ground at the very same latitude. Even inside crater floors that happened not to be permanently dark, the neutron count was normal. The hydrogen was not a general feature of the polar region. It was confined, strictly and precisely, to the places the sun had never touched. This was the answer to the question that had defeated everyone since Lunar Prospector. The question Watson, Murray and Brown had first raised 48 years earlier, without any way to test it. The hydrogen was not a thin haze of solar wind particles smeared across the sunlit polar plains. It was down inside the cold traps, exactly where the theory demanded it be, held there by the only conditions in the solar system that could hold it permanent darkness, and a cold near the edge of absolute zero. The map was not merely a detection of hydrogen, it was a confirmation of a physical mechanism drawn in data. Mitrofanov, asked later about the moment, described it simply: they saw the shadow, and they found the hydrogen sitting inside it. The results were written up and published in 2010, with Mitrofanov as the lead author and a long list of colleagues from the Moscow Institute, from NASA, and from the University of Arizona. The paper was cautious in the way careful science is always cautious, full of qualified language, of consistent with, and most likely, of error bars and ranges. The figures were color maps of the South Pole, blue and purple patches of neutron deficit nesting inside the black outlines of the permanent shadows. And the careful listener would have noticed the one thing the team did not claim. They did not claim to have proven the hydrogen was water. Their instrument counted hydrogen. It could not, by itself, tell water ice from hydrogen bound in minerals, or from solar wind protons, or from frozen methane or ammonia. The physics of cold traps made water the overwhelming favorite. Nothing else fit the pattern so well, but favorite is not the same as proven. To be certain, someone would have to reach into one of those shadows and pull out what was there. And, remarkably, a way to do exactly that was already on its way to the moon, launched on the very same rocket. It would settle the question not gently, but with a collision. The neutron map had shown, with as much precision as the instrument could manage, that hydrogen sat inside the shadowed craters. But a correlation, however perfect, is not a chemical identity. The neutrons detected hydrogen. They could not name the molecule it belonged to. To name it, you had to touch the ground itself and read what came off. And the mission built to do that would not land softly and scoop a sample. It would arrive at the darkness as a weapon. Its name was long the Lunar Crater Observation and Sensing Satellite, and its plan was audacious. It rode to the moon on the same rocket as the orbiter, still attached to the rocket's spent upper stage, a heavy, empty cylinder called the Centaur. The idea was to turn that dead piece of rocket into a cannonball. The impactor mission and its Centaur swung out into a long, looping path that carried them far past the moon and back, building up speed, and then aimed the whole thing at a permanently shadowed crater. The Centaur, weighing more than 2 tons, would strike the crater floor at some 2.5 kilometers per second a blow with the energy of a truck's worth of high explosive. The impact would blast a plume of pulverized soil, dust, and vapor up out of the shadow and, the planners hoped, high enough that sunlight streaming over the crater rim would catch it and light it up. And 4 minutes behind the Centaur, flying through the very plume its impact had raised, would come the small shepherding spacecraft, its instruments open, sampling the debris cloud, reading the chemistry of what had been buried, and transmitting everything back to Earth in the few minutes before it, too, struck the surface and was gone. The choice of target came straight out of the neutron map. The team needed a crater big enough to hit reliably, deeply shadowed, and rich in hydrogen according to the maps. Cabeus, a great crater nearly 100 kilometers wide. Near 85 degrees south was the pick. The neutron detector had measured a strong hydrogen signal over its floor. The laser altimeter's terrain model showed most of its interior lay in permanent shadow. The infrared radiometer had measured its floor at around 35 Kelvin. Cold, dark, and hydrogen-rich if excavatable ice existed anywhere in reach. Cabeus was the place to swing at. The impact was set for the 9th of October, 2009. The mission was led by Antony Koloprit, a scientist at NASA's Ames Research Center in California. The whole enterprise had been done on a shoestring, mounted quickly and cheaply as a companion to the larger orbiter. Its budget a small fraction of what a dedicated mission would have cost. Koloprit had spent years arguing that you could learn something profound about the moon by throwing a spent rocket at it and catching the splash that a crude, violent experiment, done well, could answer a question that a decade of careful orbital work had only circled. It was, in a sense, his idea being flung at the moon along with the Centaur, and in the hours beforehand his team ran their final checks. The plan had been sold to the public and the press on the promise of a dramatic, visible plume, a spray of debris that telescopes on Earth and in orbit could watch rise out of the dark. Observatories around the world turned toward the moon. A great telescope in Hawaii, the Hubble Space Telescope in Earth orbit, the orbiter overhead, and a crowd of amateur astronomers all trained their optics on Cabeus, waiting for the flash. Here it is worth slowing down and standing in that control room, because the next few minutes did not go the way anyone had rehearsed. The Centaur has already separated. It is coasting silently toward the pole, a dead cylinder of metal falling through the dark, and the shepherding spacecraft is trailing 4 minutes behind. Cameras and spectrometers open, watching the grey floor of Cabeus swell in its field of view. On the screens at Ames, the surface grows larger, sharper, the shadowed ground rushing up. The clock counts down. The Centaur strikes. And nothing happens. There is no flash on the screens. No bright fountain of debris climbing into the sunlight above the rim. The amateur telescopes, scattered across the night side of Earth, see only the same dark crater they had been staring at all along. In the control room, the team watches the feed and sees the surface simply keep rising toward the second spacecraft. No plume, no cloud, nothing, as if the 2-ton impact had been swallowed without a sound. The Centaur is gone. Its signal has ceased. The collision certainly happened, but the great visible plume, the thing the whole mission had promised, is absent. Koloprit would later call those minutes the longest of his life. The public story was already tilting, in real time, toward failure. A crater had been hit, and the moon had shown nothing. But the real measurement was never the visible plume. It was the light passing through the debris light of colors the eye cannot see. The shepherding spacecraft flew through the ejecta cloud that was there, whether or not any telescope could see it, and its spectrometers read the infrared and ultraviolet light filtering through the dust. Different molecules absorb light at different specific wavelengths, like fingerprints. Water has its fingerprints, so do carbon dioxide, ammonia, hydrogen sulfide, methane. As the spacecraft passed through the cloud, its instruments recorded which wavelengths were being swallowed, and the water fingerprints were there, not faint, not marginal clear, standing out of the spectra, unmistakable. In the days that followed, as the data were calibrated and picked over, the team put a number on it. The soil thrown up from the floor of Cabeus was something like 5.5% water by mass, give or take a few percent, and alongside the water came a whole cocktail of other frozen compounds: hydrogen sulfide, ammonia, carbon dioxide, methane, and traces of more. This was not a thin dusting, it was a genuine deposit of dirty ice, a mixture built up over billions of years from comets, from asteroids, and from the slow chemistry of the cold dark itself. The result was announced in November of 2009. After a decade of ambiguity, After a year of neutron maps that showed where the hydrogen was but could not say what it was, a single deliberate collision had settled it. The hydrogen in the cold trap of Cabeus was, in large part, water ice. The neutron map was vindicated. The 48-year-old cold trap theory was confirmed not by inference, but by direct measurement of the stuff itself. And the story that had seemed, for a few terrible minutes in the control room, to be a failure, turned out to be one of the cleaner triumphs in the history of lunar science. There is a nice symmetry buried in this. A decade earlier, Lunar Prospector had been crashed into a shadowed crater in the hope of raising a visible water plume, and had shown nothing. Now its successor had done the same thing again, with a heavier projectile and far better instruments. And this time the answer came back not in a flash of light for the telescopes, but in the quiet fingerprints of water written across an infrared spectrum. The moon had finally answered the question it had been asked twice. There is a lesson in that reversal worth holding on to. For a few minutes, in a control room in California, the mission had looked like a failure to everyone watching, because the thing the public had been promised, a bright plume, a visible splash, never appeared. The real result was arriving all the while, in a form no camera could show and no crowd could cheer, written in the invisible fingerprints of light passing through an unseen cloud. The most important measurement of the whole mission was one that looked, in the moment, like nothing at all. The spectacle failed, the science succeeded, and the two had almost nothing to do with each other. With the answer came a change in the whole meaning of the neutron map. It had been a map of hydrogen. Now, at least where it had been ground-truthed, it could be read as a map of water. The question stopped being whether the moon had water. It became a different question entirely. How much, and where exactly, and could anyone reach it? Cabeus was not the only place the old idea of a bone-dry moon was collapsing that year. While the neutron team built their case at the poles, water was turning up across the rest of the moon too, found by other scientists using other tools, and the timing was almost eerie. The dry moon, a belief that had stood since Apollo, fell on several fronts within the space of a couple of years. The first blow came from the Apollo samples themselves, the very rocks that had established the dry moon in the first place. In 2008, a team led by a geologist named Alberto Sal took a fresh look at those tiny beads of volcanic glass, the orange and green droplets sprayed from ancient fire fountains, using instruments far more sensitive than anything available in the 1970s. They found water dissolved inside the glass, not much, but far more than zero, and arranged in a way that suggested the moon's deep interior had held water when that glass erupted billions of years ago. The samples had not been wrong. They had simply been read with tools too blunt to catch what was there. The moon had been born with at least some water inside it after all. The second blow came from orbit, and it arrived almost at the same moment as the impact into Cabeus. An instrument built by NASA and flown on India's first lunar orbiter had been mapping the minerals of the lunar surface by the sunlight they reflected. Led by a scientist named Carl Peters, the team found, across broad stretches of the sunlit moon, the faint spectral fingerprint of water and hydroxyl bound into the surface, soil-thin, widespread, strengthening toward the poles. This was the solar wind water, the film the sun slowly manufactures across the whole lunar face, caught at last in the act. Older data from passing spacecraft, re-examined, showed the same thing. Within a single year then, water had been found dissolved in the ancient interior, spread thinly across the sunlit surface, and concentrated richly in the polar shadows. The dry moon was not merely wrong at the poles, it was wrong nearly everywhere, in 3 different ways at once, and of the 3, only one mattered for the future of spaceflight: the concentrated ice in the cold traps, the one deposit rich enough and reachable enough to fuel a journey, which returns us to the map. One impact told you about one spot. Cabeus was a single crater among dozens of shadowed floors scattered around the South Pole, and the neutron map already showed that they were not all alike. Some held far stronger hydrogen signals than others. If the moon was ever going to be a place people worked and refueled, you needed more than a single confirmed deposit. You needed an inventory. Which craters held the most? How the ice varied from one to the next, where a lander could set down within reach of a rich, dark floor. That task fell back to the neutron detector, still circling overhead, still gathering counts on every pass, its map growing sharper with every added month of data. Over several years, Mitrofanov's team, with a colleague named Anton Sanin leading much of the analysis, turned the accumulating counts into a detailed hydrogen map of the whole South Polar region. It was, in a real sense, a first-of-its-kind resource survey of another world, drawn from orbit, showing where the most accessible water was likely to lie. And it revealed a South Pole that was not uniformly icy but speckled, a scatter of rich deposits separated by dry ground, like islands in a barren sea. A few of those islands are worth knowing by name, because they have become the addresses of the coming lunar age. Cabeus, the crater the impactor struck, was the anchor point, the one place where the neutron reading had been checked directly against the water measured in the plume. Its hydrogen was not spread evenly across its floor, but concentrated in patches, richer here, thinner there, reflecting the uneven history of how ice had arrived and settled. Calibrated against the impact result, its floor worked out to somewhere around 3 to 5% water by mass in the upper meter of soil. That sounds small until you hold the volume in your mind. Heat a single cubic meter of that soil, a block the size of a washing machine, drive off the water, and you might collect a full bucket of it, and Cabeus covers hundreds of square kilometers. Shoemaker, named for the same Eugene Shoemaker, whose ashes had ridden Lunar Prospector to the moon, showed a hydrogen signal stronger even than Cabeus, one of the strongest anywhere at the pole. It is an old crater, its floor pocked by later impacts, its shadow deep, and its temperature down, where no water molecule could ever gather the energy to escape. Anything that fell into Shoemaker in the last few billion years is, most likely, still there, locked in place for longer than complex life has existed on Earth. It is worth letting that timescale settle. The ice at the bottom of these craters is not recent. Some of it may have arrived before there were animals on Earth, before there were plants, when life here was still nothing but single cells in the sea. It has sat in the dark, untouched, through the entire rise of everything we would recognize as living through the fish and the forests, the dinosaurs and their extinction, the slow emergence of our own kind. Whole eras of Earth's history have passed while that ice simply waited in the shadow, a few 100,000 kilometers away, changing not at all. And the first machine to dig into it will be disturbing something that has been still since before the beginning of the story we tell about ourselves. Haworth is one of the coldest places anyone has ever measured. Parts of its floor read colder than the surface of Pluto. At a temperature like that, it is not only water that freezes out and stays even carbon dioxide, even methane, compounds that would slowly escape from the merely very cold floors of other craters, can be held fast. Haworth may be less a store of water than a store of everything, a frozen library of the whole chemistry that has rained onto the moon across its history. Faustini offered a different lesson. Rather than one great smooth floor, it holds a jumble of smaller shadowed pockets, cold traps within the crater created by the overlapping rims of lesser impacts. And the neutron detector saw hydrogen in those small pockets, too proof that the trapping mechanism did not need a giant crater to work. A shadow only a few kilometers across, if it was truly permanent, could gather and hold its own ice. That mattered for anyone planning to mine it, because it meant the water was not confined to a handful of enormous basins, but distributed across many smaller sites, some of them easier to reach. And then there is Shackleton, which is special, and which became a genuine puzzle. Shackleton is a crater sitting almost exactly on the South Pole, its rim tracing the very bottom of the world. Because of where it sits, its rim catches nearly continuous sunlight, a near-perfect peak of eternal light. an obvious place to plant solar panels for a future base, while its floor lies in permanent shadow. By every expectation of the cold trap theory, Shackleton's floor should have been rich with ice. It became, for years, the poster crater of lunar polar exploration, the place everyone pictured when they imagined humans returning to the moon to find water. But the neutron detector saw only a modest signal there, weaker than Cabeus, weaker than Shoemaker, weaker than several planar craters nearby. And radar instruments, which look for the particular echo that thick, clean slabs of ice return, saw no clear sign of such slabs on Shackleton's floor at all. An Indian orbiter carrying its own radar, flying a little earlier, had returned much the same puzzle. The crater that ought to have been the richest was strangely poor. No one is certain why. Perhaps it is younger than its neighbours and has had less time to gather ice. Perhaps its brightly lit rim radiates just enough heat down onto the shadowed floor to let a little of the ice slowly escape. Perhaps the ice is there but hidden, dispersed as thin coatings on soil grains, rather than gathered into the thick lenses that radar can catch. The debate is still open, and Shackleton remains one of the most studied and most argued over patches of ground on the moon, a standing reminder that the map is real, but the fine detail is not yet understood. Here, though, the story has to be honest about a quieter controversy, because it is part of what makes the science real rather than a fairy tale. Not everyone was convinced the collimated neutron sensor worked as sharply as its makers claimed. In the years after the maps were published, some scientists, including researchers with deep experience from Lunar Prospector's own neutron instrument, analyzed the detector's behavior and argued that a large share of the neutrons it counted were not, in fact, coming through the narrow shielded aperture at all. They argued that neutrons were leaking in from other directions, that the true sharpness of the collimated view was less than advertised, and that some of the crater-scale detail on the maps might be softer and blurrier than it appeared. Mitrofanov's team defended their instrument and their analysis. The critics pressed their case. Papers went back and forth. This is not a footnote to be embarrassed about. It is how the field does its work. A genuinely difficult measurement, made at the edge of what the instrument could do, tested and retested by people with every incentive to find the flaws. It matters, too, for how anyone plans to use the map, because a mission designer betting a lander on a particular crater needs to know not just where the map says the water is, but how much to trust that particular pixel. A map that is sharp and reliable lets you aim for a small, rich target with confidence. A map that is softer and blurrier than it looks tells you to hedge, to pick broader targets, to send a scout before you commit a base. The argument over the instrument's true resolution is, underneath the technical language, an argument about exactly that, about how boldly the coming missions can act on what the map appears to show. And it is a healthy argument to have before landers start descending, rather than after. The broad result held. Hydrogen is concentrated in the shadowed craters, and the impact confirmed it as water, but the exact numbers, crater by crater, still carry an argument inside them, and any honest map of the lunar water has that argument printed faintly across it. The neutron detector, meanwhile, simply kept working. It had no moving parts to wear out, no coolant to run dry, no mechanism to jam. It just counted, pass after pass, year after year, far longer than anyone had planned for. There is a particular virtue in an instrument built this simply. A camera can have its optics fog or its shutter stick. A drill can seize. A robotic arm can freeze at a joint. The neutron detector has almost nothing that can fail a shield. Some tubes of gas, and the electronics to count pulses. And so, while flashier machines came and went, while landers crashed and rovers were cancelled and missions rose and fell, this one quiet box kept doing the same patient thing it was built to do, adding row after row to a record that grew more valuable simply by lengthening. A single map of the pole is a snapshot. A record spanning more than a decade is something better. A slow film, capable of showing not just where the hydrogen sits, but whether it shifts, whether the polar volatiles breathe in and out with the long rhythms of the Sunday, almost by accident, in outlasting its own mission many times over, the instrument stopped being a map maker and became a historian, and as its record lengthened, the statistics firmed up, fainter deposits climbed out of the noise, and smaller cold traps became visible shadows within shadows. The South Pole came into focus, not as a single ice sheet, but as an archipelago of frozen ground, a scatter of resource islands that a rover could, in principle, drive between, letting a future crew choose a landing site within reach of several water sources at once. This changes how you would plan a base. You would not simply aim for the single richest crater and set down inside it a permanently shadowed floor is a terrible place to live, with no sunlight for power and a cold that fights every machine. Instead, you would look for a spot on a sunlit ridge, a peak of eternal light for your solar panels and your habitat, positioned so that 1 or 2 or 3 ice-rich shadows lay within a manageable drive. You would live in the light and mine in the dark, shuttling between them. The map, read this way, is not just a survey of where the water is. It is a survey of where a settlement could stand a scatter of possible addresses, each one weighed by how much ice lies nearby and how easily a machine could reach it and haul it back up into the sun. One number, though, stubbornly refused to sharpen: the total. How much water is actually down there, added up across the whole pole? The honest answer is that no one knows within a factor of about 10. Turning a neutron count into a quantity of water means assuming how the hydrogen is arranged in the soil, whether it lies in an even layer, or hides beneath a dry crust, or is mixed unevenly through the ground. And different reasonable assumptions give answers that differ enormously. Depending on which you choose, the South Pole holds either a large but finite reserve, something to be managed carefully over decades, or a supply so vast it is effectively bottomless on any human timescale. For a single mission that needs a few tons of water, the difference does not matter. The resource is plainly big enough. For the question of whether the moon can support a permanent, growing human presence for centuries, the difference is everything. And it is a difference that cannot be settled from orbit, no matter how long the detector counts. To settle it, you have to land and drill and measure the ground directly. The map had done everything a map can do. The next step was to go. To understand why the ice matters so much, you have to understand what it costs to bring water from Earth, and to feel that costs the way an engineer feels it. Every kilogram lifted off the surface of our planet has to be accelerated to enormous speed simply to reach orbit, and to go all the way to the surface of the moon, it must be accelerated further still, and then lowered gently down against the moon's own gravity. The tyranny that governs all of this is the rocket equation, and it is merciless. Most of the mass of any rocket standing on the launch pad is propellant. The actual payload, the thing you want to deliver somewhere, is a small fraction of the whole, a sliver at the very top. And the farther you want to send that sliver, the smaller it gets, because you must burn fuel to carry the fuel that carries the fuel. By the time you have delivered 1 kilogram of anything to the lunar surface, you have spent a sum well into 6 figures to do it. A litre of water weighs a kilogram. So a litre of water on the moon, carried up from Earth, is worth more than a car. Fill a bathtub, and you have spent more than the price of a house. This is not a failure of engineering that a cleverer rocket will fix. It is physics. The energy packed into chemical fuel is fixed by chemistry. The depth of Earth's gravity well is fixed by Earth's mass. There is no trick that escapes the arithmetic. There is only paying it. Every gram of water, every gram of food, every brick and bolt and breath of air a lunar settlement might need has to be either hauled up from Earth at this ruinous price or found on the moon itself. That single fact is why Apollo was a set of brief visits rather than the beginning of a settlement, and why, for decades afterward, a permanent lunar base stayed firmly in the realm of imagination. You cannot build a town where every brick costs its weight in gold. The water in the shadows breaks the arithmetic, not by changing the physics, but by removing the need to pay it. A water molecule on the moon is exactly the same as a water molecule on Earth, two hydrogens bound to an oxygen. But water that is already there does not have to be launched. It only has to be dug up. And so the whole logic flips. Instead of carrying water, you carry the machine that extracts it. This idea has a clinical name in the planning documents, using local resources instead of imported ones. But the substance of it is simple and old. Live off the land. And on the moon, living off the land means far more than drinking. Pass an electric current through water, and it comes apart into its two elements, hydrogen gas and oxygen gas. That process, electrolysis, is ordinary school children do it in chemistry class. But on the moon, its two products are treasure. Hydrogen, kilogram for kilogram, is the most energetic chemical rocket fuel there is. Oxygen is what you burn it with, and it is also, of course, the gas a human being has to breathe. Split a single liter of water and you get something more than 600 liters of oxygen at ordinary pressure, roughly a day's breathing for one person, together with a quantity of hydrogen that, burned back together with that oxygen, releases a real jolt of energy. In space, water is not just something you drink, it is stored power. It is a battery, a fuel tank, and a life support supply, all frozen into the same grey soil. This is where the shape of a new kind of spaceflight comes into focus. Imagine a ship leaving Earth with its tanks only partly filled enough fuel to reach the moon, and no more. It descends near the South Pole, or meets a station in lunar orbit fed from the surface below, and there it takes on water dug from the permanent shadows. That water is split into hydrogen and oxygen, chilled to liquid, and pumped into the ship's tanks. Now the ship is full, but it filled up 250,000 kilometers from Earth, having never paid to lift that fuel out of Earth's deep gravity. From there it departs for Mars, or the asteroid belt, or the moons of the outer planets, carrying a full load it did not have to launch. Think of it the way a pilot thinks about crossing a wide ocean. If there is no place to refuel along the way, the aircraft must carry every drop of fuel for the entire crossing from the very start, and fuel is heavy, so it must also carry the fuel to lift that fuel, and the crossing becomes barely possible, achievable only by enormous machines stripped of everything but tanks. But put a single island with a fuel depot halfway across, and the whole problem softens. Now the aircraft need only carry enough to reach the island. It lands, fills up, and continues, and the journey that was barely possible becomes routine. The moon is that island. The ocean is the gulf between Earth and Mars, and the water in the shadows is the fuel depot that turns an almost impossible crossing into a series of manageable hops. This is the filling station model, and its savings are not marginal. A Mars expedition mounted entirely from Earth demands a colossal rocket, because every drop of fuel for the whole journey has to be heaved off our planet at once. Source the fuel at the moon instead, and the part you launch from Earth shrinks dramatically. You need only reach lunar orbit. The moon carries you the rest of the way. To feel the scale of what the map promises, hold two numbers side by side. On one side, the cost of lifting fuel from Earth, hundreds of thousands of dollars for every kilogram delivered to the lunar surface, a price that makes any fuel launched from Earth almost too precious to burn. On the other side, the estimates of what waits in the shadows, even at the cautious end. The polar craters are thought to hold water measured not in liters or tons, but in hundreds of millions of tons, and possibly far more. Set against the need a lander that must refuel might want a few tons of water. A small base, perhaps hundreds of tons a year. The resource is not merely adequate. It is, on any human timescale, effectively without limit. The whole calculation of what is possible beyond the Earth changes when the fuel is already at the destination, sitting in the ground, waiting only to be dug and split. A voyage to Mars stops requiring a rocket the size of a skyscraper launched in a single heave, and becomes instead a series of shorter hops, each one topped up from a tank that Earth never had to fill. That is the promise. The difficulty of actually collecting the water is just as real. And it starts with the soil. Lunar regolith is not friendly stuff. It is a fine grey powder ground out of solid rock by billions of years of micrometeorite strikes. And because there has never been wind or water to smooth it, its grains are sharp, jagged, glassy little shards, some barely larger than smoke particles. They carry an electrostatic charge that makes them cling to everything. The Apollo astronauts learned this the hard way. After every moonwalk, their suits came back caked in grey dust that would not brush off, that ground into the joints of their equipment and the seals of their sample bags, that got into the cabin and, exposed to the air inside, smelled faintly of spent gunpowder and caught in their throats. Any machine meant to dig and process this soil for years must survive being scoured, jammed, and infiltrated by a dust engineered by nature to destroy moving parts. And the water is not sitting in a convenient underground lake waiting to be pumped. In most places, the evidence points to ice bound intimately into the soil, filling the tiny spaces between grains like a frozen cement, or coating the grains themselves, or simply mixed through as scattered frozen crumbs. To get it out, you would have to dig up the frozen soil, carry it to a sealed chamber, heat it until the ice turned to vapor, and then catch and cool that vapor back into liquid water, all of it in vacuum, all of it starting from a cold near the bottom of the temperature scale, all of it done by machines light enough to launch and tough enough to run for years without a repair crew. The heating needs energy, and energy on the moon means sunlight, and this is where the peculiar clock of the moon becomes decisive. Almost everywhere on the lunar surface, the day and the night each last about 2 Earth weeks, 14 days of unbroken sunlight, followed by 14 days of unbroken dark and brutal cold. For any machine that runs on sunlight, that is close to fatal. It would have to store 2 weeks of power to survive each night, or shut down and freeze until dawn. A digging and processing operation that stalled for a fortnight every month and had to be nursed back from deep cold each time would barely function. But the poles escape this trap. On the high ground at the pole, those peaks of eternal light, the sun does not set for 2 weeks at a time. It circles the horizon almost continuously, so a solar panel placed there sees sunlight nearly without interruption, year-round. That near-constant power is what makes the pole not just a place with water, but a place where you could actually run the machinery to extract it. The ice is in the dark. The power is in the light. And at the pole, uniquely, the two lie within reach of each other. This is where those peaks of eternal light beside the shadows turn from a curiosity into a plan. Ring the poles high, sunlit ground with solar panels. Run the power down into the dark and drive the diggers and the ovens with it. Some designs skip the electricity entirely and use great mirrors to focus raw sunlight straight onto the frozen soil, boiling the ice out directly and funneling the steam into a cold trap to collect. Others propose beaming microwaves into the ground to heat the ice from within. Every one of these schemes is possible in principle. Not one has yet been demonstrated on the moon. The engineering that this demands is genuinely new. No one has ever built a mining machine that works in vacuum, at temperatures near the bottom of the scale, in 1/6 of Earth's gravity, on power that vanishes for 2 weeks at a time if you stray from the sunlit ridges, choked all the while by a dust engineered to destroy it. Every ordinary assumption of terrestrial mining fails. There is no air to carry heat away, so machines overheat in ways they never would on Earth. Lubricants freeze or boil off. The low gravity means a digger cannot simply press down with its weight to bite into the ground. It may lift itself off the surface instead. Water vapor driven from heated soil will try to refreeze on every cold surface it touches, coating the very machinery meant to collect it. Each of these is a solvable problem, and teams on Earth are working through them now, testing prototype diggers and ovens on simulated lunar soil in vacuum chambers. But solvable on Earth and proven on the Moon are two different things, separated by exactly the kind of gap that swallowed Lunar 25. Nor will the water come out clean. The impact into Cabeus showed the ice laced with hydrogen sulfide, ammonia, carbon dioxide, methane. Some of these are not waste but bonus. The ammonia carries nitrogen, which is scarce on the Moon and vital for growing food. The carbon dioxide, combined with hydrogen, can be turned into methane, another usable fuel. There is a broader picture in that cocktail, and it changes how you think about the resource. The shadowed craters do not hold pure water. They hold a frozen mixture of nearly everything volatile that has ever reached the Moon water. Yes, but also carbon compounds, nitrogen compounds, sulfur compounds, the raw chemical building blocks of air, fuel, fertilizer, and plastics, for a settlement that is closer to a general store than to a single commodity. The water gives you drink, breathable oxygen, and rocket fuel. The nitrogen, drawn from the frozen ammonia, gives you a component of breathable air and a nutrient for growing plants, and nitrogen is genuinely scarce on the Moon, so a source of it is precious out of proportion to its quantity. The carbon compounds give you the makings of fuels and, with the right chemistry, of materials. A cold trap, seen this way, is not a well. It is a warehouse, stocked over billions of years, holding a rough version of most of the raw ingredients a human outpost would need to stop importing and start making its own supplies. But every one of those useful compounds is also, from the point of view of the water, an impurity that must be stripped out before the water can be drunk or split, and every step of that cleaning adds mass and complexity to the machine. And once machines have proven they can do all this reliably, and people finally arrive to stay, the same frozen ground offers something else. Water itself is an excellent shield against the radiation that pours unfiltered onto the airless Moon, because its abundant hydrogen absorbs the high-energy particles well. A tank of water wrapped around a habitat, and a mound of regolith piled over its roof, could bring the radiation inside down to something a human body can live with for the long term. This matters more than it might sound, because radiation is one of the quiet, patient dangers of living off the Earth. On the Moon there is no thick atmosphere and no protective magnetic field to soften the constant sleet of cosmic rays, or to shield against the sudden violent bursts of particles that the Sun occasionally throws out. A crew exposed to that for months or years would accumulate a dose no one would accept on Earth. The frozen water in the ground offers a defense not because anyone planned it that way, but simply because the physics that lets hydrogen betray water to a neutron detector is the same physics that lets water soak up dangerous radiation. The very property that made the ice findable makes it protective. The South Pole, in other words, is not only a filling station, it is a quarry, a reservoir, a radiation shield, and a construction site, all in the same grey ground, none of which changes the fact that to use any of it, you first have to land, and landing at the South Pole, it turned out, was about to prove how unforgiving the Moon can still be. On the 10th of August, 2023, a Soyuz rocket rose from a cosmodrome in the far east of Russia, carrying a spacecraft called Lunar 25. It was the first Russian lunar lander in 47 years, the first since Lunar 24, which had scooped a sample of lunar soil and flown it home in 1976, back when the Soviet Union still existed. That older lunar program had once written some of the proudest lines in the history of exploration. The first spacecraft to fly past the Moon, the first to strike it, the first to land softly upon it, the first to return a sample by robot. Then, for nearly half a century, silence. Lunar 25 was meant to break that silence, and to do something none of its ancestors had done to land near the South Pole. On the edge of the terrain the neutron map had made famous, and to drill into the polar soil and taste the volatiles inside it. It was, in the most direct possible sense, the mission that would close the loop the neutron detector had opened. It would bring ground truth to the map. The spacecraft was small, under a ton in dry weight, carrying a robotic arm, a drill able to reach a little way beneath the surface, and instruments to analyze whatever the drill brought up. Its landing site sat at high southern latitude, near a crater named Boguslavsky, chosen because it was close to the pole, gentle enough to land on, and marked by hydrogen in the neutron data. The launch went well. The Soyuz placed Lunar 25 into orbit around the Earth, and from there the lander fired its own engine and set off across the gap to the Moon. The crossing took several days. It slid into lunar orbit healthy, its systems working, and its controllers began preparing for a landing set for a few days later. Before descending, the spacecraft had to trim its orbit a series of engine burns to lower and shape its path for the final approach. And it was during one of these routine burns that Lunar 25 was lost. The engine was commanded to fire for a set, careful interval and then shut down. It fired. It did not shut down. Instead of the short, precise burn the plan called for, the engine kept thrusting, far longer than intended, and the extra push flung the spacecraft off its careful path and down toward the surface on an uncontrolled trajectory. Contact was lost. Controllers called and listened and heard nothing. Lunar 25 had struck the Moon and was gone. The Russian Space Agency confirmed it the next day in a brief, bleak sentence. The spacecraft had ceased to exist as a result of a collision with the surface. A later investigation traced the failure to a sensor in the propulsion system that had failed to send the command to stop the burn. The engine had simply run on until the fuel that fed it was spent, and the spacecraft fell. For Igor Mitrofanov and the team at the Institute, the loss cut deep. Even though the lander itself had been built by a different organization, the old Soviet-era spacecraft house that had made the original lunar probes, the science aboard was bound up with everything the neutron detector had begun. Mitrofanov had waited decades for this landing. He had mapped the water from orbit. He had watched the hydrogen signatures rise out of the data, year after patient year. He had watched American, Chinese, and Indian missions take his maps and use them to plan their own journeys to the pole. And now the one mission that was to have been Russia's own hand laid on the ice, the closing of a loop he had personally opened, was scattered across the lunar surface. In interviews afterward, he spoke with a kind of hard-earned steadiness, the calm of someone who has spent a career learning that the universe does not arrange itself around anyone's plans. The Moon, he said, is unforgiving. He was careful to point out that this was not a failure of the science. The neutron detector had worked flawlessly for well over a decade, and its data would go on guiding missions for years. But the weight of the disappointment was plain underneath the composure. Russia had mapped the water. Russia had not yet touched it. The map was a triumph. The reaching for the thing itself had ended in a crater. The crash was not only a Russian loss, it was a warning to everyone. Landing near the lunar South Pole is genuinely harder than landing near the equator, where every successful soft landing of the 20th century had come down. Consider what a lander's automatic systems face there. Near the equator, where every 20th century landing came down, the sun is high, the light is even, the ground is relatively flat, and a spacecraft's cameras and sensors see the surface clearly as they pick a safe spot to touch down. At the pole, the sun grazes the horizon, so shadows are enormous and stark. A small rock can throw a shadow many times its own length, and a lander, trying to read the ground below, can mistake a harmless shadow for a pit, or fail to see a genuine boulder hidden inside the dark. The terrain itself is rougher, cut with ridges and craters where a flat pad is hard to find. The angles for talking to Earth are lower and more awkward, so communication is harder to hold, and the whole descent must be flown more precisely, because the safe spots are smaller and farther between. Every one of these makes the last few minutes always the most dangerous part of any landing more dangerous still. The margin for error, thin everywhere in spaceflight, narrows at the pole to almost nothing. The difficulty is not theoretical, and the point was driven home with almost unbearable timing. Just days after Lunar 25 fell, an Indian lander, Chandrayaan-3, touched down safely at a very similar high southern latitude, becoming the first spacecraft ever to land intact in that region. Two nations, aiming at nearly the same forbidding ground within the same week, one succeeding, one failing. The moon offered no explanation and played no favorites. It simply enforced its own hard standard. There is a deeper lesson folded into the crash, and it is the lesson that runs under this whole story. The discovery of the water was a triumph of looking of orbital science, of clever instruments reading invisible signals from 100 kilometers up. But looking can only take you so far. To turn a map into a resource, you have to land and dig and process, and every one of those steps opens a fresh chance to fail. The ice is real. Its location is known to within a few hundred meters, but the distance between knowing where the water is and being able to lift a single cup of it to your lips remains enormous. And Lunar 25 fell into exactly that gap. And Lunar 25, for all the weight of its loss, was only one boat in a sudden crowd of them. After half a century in which the moon was almost abandoned, the South Pole has become, in the span of a few years, the most sought-after ground off the Earth. India, days after the Russian crash, set its lander gently down and became the first nation ever to reach the South Polar region intact. Private companies, flying under contract to NASA, have begun sending robotic landers of their own toward the pole, one of them touching down not far from that region and becoming the first American craft to land softly on the moon since the last Apollo crew left, even as it tipped onto its side on the rough ground, a small emblem of how hard this terrain still is. China, which has become the most methodical lunar power of the age, has landed repeatedly on the moon, returned samples from its far side, and laid out a deliberate program of missions aimed squarely at the South Pole and its water, building toward a permanent research station there in partnership with Russia. The United States, through its Artemis program, intends to land astronauts near the South Pole, the first human beings to walk on the moon in over half a century, and the first ever to walk at the pole, guided to their landing sites by the same neutron maps this story has followed. Not every plan will survive contact with reality. Budgets shift, rockets slip, robotic scouts get cancelled before they fly. But the direction is unmistakable. Everyone is going to the same place, for the same reason, following the same map. In the months after the crash, Russia announced further missions to try again what this one could not, and then, under the strain of budgets and isolation, quietly let their schedules slip. The pole, which had seemed so close when the maps were fresh, drew back a little not because the science had changed, but because the machinery of reaching it had faltered. And yet the water is still there, waiting in the dark, exactly where it was. The instrument that found it is still in orbit, still counting. The story did not end with the crash. It only revealed how much of the story is still to come, because the moment the ice became real, it stopped being only a scientific question and became something older and more complicated, a thing that nations want. The maps are in hand, the water is real, the craters have names and coordinates and rough concentrations. A spacecraft has struck the darkness and read the water in the debris, and yet, for all of that, the ice is still, in many ways, a stranger, because knowing that it exists is very different from knowing what it is like, and almost everything that would let us actually use it remains uncertain. The most basic unknown is the physical form of the ice. The neutrons detect hydrogen, and from hydrogen we infer water, but that inference says nothing about how the water is arranged. Is it a delicate frost coating the soil grains? A frozen cement filling the pores between them? Scattered chunks mixed through the dirt like raisins in a cake? Or, in some places, a thick, relatively clean slab of ice buried under a dry lid of soil? Each of these would demand a completely different machine to extract it. A frost you could bake out with gentle heat, a cement you would have to crush and cook, a buried slab you might drill and pump, more like an oil well than a quarry. Until someone knows which of these the ice actually is, and it may be different in different craters, no one can finish designing the equipment or honestly estimate what it would cost in energy to run. The radar readings only deepen the puzzle. On Earth, thick, clean ice returns a bright, distinctive radar echo, and instruments flown to the moon looked for exactly that echo in the shadowed craters. In most places, they did not find it, even in craters where the neutrons clearly showed hydrogen. That absence does not mean the ice is missing. It more likely means the ice is not in thick, clean slabs at all, but mixed intimately with soil, so that the radar sees a jumbled mess of rock and ice rather than a smooth reflector, or that it lies buried under dry soil that soaks up the radar before it can reach the ice, or that it is a strange, disordered form of ice, laid down molecule by molecule in the deep cold, that simply does not answer radar the way ordinary crystalline ice does. Neutrons say hydrogen is there. Radar says it is not there as clean ice. Both can be true at once, and reconciling them is one of the live problems of lunar science. The depth of the ice is unknown too. The neutrons only sense the top meter or so of soil. Below that, the detector is blind. The ice might thin out just beneath, or it might run down for many meters. Some models suggest the poles hide a dry crust, a lag of desiccated soil at the very surface, stirred and baked by tiny impacts until its ice escaped, lying over richer ice below. If that crust exists, it would set a cruel trap for the first machines. A rover scooping the surface might come up with nothing but dry dirt, while ice sat waiting just half a meter down, out of reach of a shallow scoop. And why the deposits differ so wildly from one cold crater to the next, why Cabeus is wet, Shoemaker wetter, Shackleton oddly dry is not understood either. It comes down to the accidents of history, to which comets struck where and when across billions of years, and to the individual histories of each crater, how old it is, how deep, how well its rim keeps out the last stray warmth of the low Sunday. The ice at the poles is not a single event, but a running total of everything that has happened there since the traps went cold, and running totals are hard to read backward. We can see the sum. We cannot yet break it into the terms that made it. There is also the question of what a mining machine would actually meet when it started to dig. And here the uncertainty is not academic, but immediate and practical. If the very top layer of soil has been stirred and baked dry by the endless rain of micrometeorites, leaving its ice concentrated only below, then the first scoop of any lander might come up disappointingly dry, tempting its operators to conclude, wrongly, that there was nothing there. The richest ground might lie half a meter or a meter down, past the reach of a shallow scoop, demanding a drill instead of a shovel. A mission that arrives expecting to skim ice off the surface could fail not because the ice is absent, but because it guessed wrong about the depth, until a machine actually digs into a polar cold trap and reports back what it finds at each level. That guess remains exactly that, a guess, with a great deal riding on it. These are the ordinary growing pains of a young science. First, you detect a thing, then you map it, then you learn what it is, then you learn to use it, and each stage takes its own decades. But at the South Pole, the scientific questions have become tangled with a second set of questions that have no clean precedent at all. Questions not about physics, but about law and ownership, and who is allowed to take what. This is where a different kind of expert has entered the story. As the reality of the ice has sunk in, it is no longer only planetary scientists studying the pole, but lawyers, economists, and policy scholars. People who study not what the moon is made of, but what human beings are permitted to do with it. And they keep returning to a document written when all of this was science fiction. The Outer Space Treaty, agreed at the height of the Cold War and signed by the United States, the Soviet Union, and dozens of other nations, laid down two principles that have governed space ever since. First, that no nation may claim ownership of the moon or any other body in space. You cannot plant a flag and declare a crater your sovereign territory. Second, that the exploration and use of space shall be carried out for the benefit of all countries. Those principles were written to stop the Cold War powers from carving up the heavens the way empires had once carved up the earth. But the treaty is silent on the question that now matters most. It says, a nation cannot own the moon. It does not say whether a nation or a company can mine the moon, dig up its water, keep what it extracts, and sell it. It does not define where use, which is permitted, ends and appropriation, which is forbidden, begins. When the treaty was written, no one imagined a robot drilling ice from a crater floor to fuel a ship bound for Mars. The negotiators were worried about nuclear weapons in orbit and military bases on the surface, not about who owns the water in a permanently shadowed crater. A later agreement, in the 1970s, tried to fill the gap by declaring the moon's resources the common heritage of all humankind and calling for an international body to govern their use. But the major spacefaring powers, the United States and Russia and China among them, refused to sign it, and it withered into a dead letter with no force behind it. So, in the absence of any agreed law, nations have begun writing their own. The United States passed legislation declaring that American companies may own and sell the resources they extract from bodies in space. The small nation of Luxembourg passed a similar law, positioning itself as a home for space mining ventures. A set of agreements led by the United States, now signed by dozens of countries, affirms the right to extract and use space resources and tries to set shared rules of conduct at the pole. Russia and China have declined to sign those and are pursuing their own joint framework for a research station at the lunar South Pole. 2 blocks, 2 sets of rules, no binding agreement that reconciles them, and both of them planning to land at the same small region of the same small pole, drawn to the same handful of ice-rich craters, because that is where the neutron map says the water is. What makes this genuinely difficult, and not just a lawyer's abstraction, is the peculiar geography of the resource. The water is not spread evenly over the moon, free for anyone to gather anywhere. It is concentrated in a handful of specific craters at one specific pole, and the best of those craters sit beside the best sites for a base, the peaks of eternal light, where the sun and the ice lie close together. There are only so many of these prime locations. They are, in the language of economics, scarce and rivalrous. If one operation occupies the best ground, another cannot. And they are exactly the places every nation and company is aiming for, because the map tells them all the same thing. A treaty that forbids owning territory, written for a moon imagined as endless and empty, meets a reality of a few precious plots that everyone wants at once. The rule against appropriation was meant to keep the moon from being carved up. It did not anticipate a moon where the valuable part is so small and so crowded. The collision is not hypothetical, and the scholars who study this see it coming. If one nation's robots begin extracting ice from Shoemaker Crater, and another nation's robots arrive a few years later wanting to work the same floor, what happens? Does being first create a claim, in defiance of the treaty that forbids claims? Does the rule against appropriation forbid a country from fencing off the patch it is mining, and if it does, what stops 2 operations from interfering with each other on the same ground? Or will the simple physical fact of a limited resource in a limited place force the nations into some kind of coordination, ready or not? No one has the answers. They will be worked out, for better or worse, in the next decade as the landers arrive. And there is a quieter argument still, one that the planetary scientists raise among themselves. The permanently shadowed craters are among the most pristine places in the solar system. They have sat cold and undisturbed for billions of years, and the ice inside them is not only a resource, it is a record, a frozen archive of the volatile history of the inner solar system, of every comet and every chemical process that delivered water to this corner of space across the age of the planets. To mine that ice is to destroy the archive, irreversibly, one shovelful at a time. Some scientists have begun to argue that at least one major cold trap should be set aside and protected, studied, never touched, kept as a library for a future generation with better questions and better tools, before the first mining machines begin turning the record into fuel. Others answer that the practical need to use the resource to open the solar system to human beings outweighs the loss. The debate is still quiet, It will not stay quiet as the first machines approach the shadows with their drills. All of it, the unknown form of the ice, the empty spaces in the lore, the tension between mining and preserving rests on top of the neutron map. And the map itself is silent on every one of these questions. It shows where the hydrogen is, with its error bars and its contours and its faint printed argument about how sharp the view really was. It does not say who should own the water, or how fast to take it, or whether some of it should be left alone forever. Mitrofanov's team built an instrument to answer one clean scientific question. Is there water ice at the moon's south pole? The answer came back, yes. The instrument, still circling after more than a decade, is still refining that yes. But the question has long since outgrown anything a neutron detector can address. The ice is there, the maps are drawn, the landers are being built. What happens next is no longer a question for physics. It is a question for us. You are standing in a crater at the moon's south pole. The sun has not touched this floor for 2 billion years. The temperature is minus 240 degrees Celsius. There is no sound, no wind, no light except the faint wash of stars and the blue-green crescent of Earth hanging low on the rim. You could walk across this regolith and leave prints that would last longer than the human species has existed. But you know now what lies beneath your feet. Not a guess, not a theory, not the hopeful arithmetic of an earlier age. You know because a box of detectors, the weight of a large suitcase, built in a laboratory in Moscow, bolted to the flank of an American spacecraft and pointed down into the dark, measured it. You know because neutrons, born when cosmic rays shattered the atoms of the lunar soil and then slowed by their collisions with hidden hydrogen, carried a message up out of the ground to a set of helium-3 tubes in orbit, a message that said, in the only language it had, that there was water down there, a few percent by mass in the upper meter of rock, enough to fill the tanks of rockets that have not yet been built. It took decades to walk from the first hint to the proof. William Boynton caught the polar hydrogen signal in the Lunar Prospector data and could not tell whether it came from the shadows or the sunlight. Igor Mitrofanov built a shield that could narrow a neutron's view to a single crater, and his instrument mapped the pole finely enough to see the ice sitting inside the dark. Antony Koloprit threw a spent rocket stage into Cabeus and read the water in the plume that no telescope could see. The lander that was meant to reach down and touch the ice directly fell instead into the surface, a reminder that the moon still gives up nothing easily, and the instrument that started all of it is still up there, circling every 2 hours, still counting, adding to a record that will outlast the governments that launched it. The ice is a fact now. It is no longer a question. And because it is a fact, the moon is no longer the world it was when the Apollo astronauts walked across it and carried home their dry, grey rocks. The moon of Apollo was a destination, a place you reached, stood upon, gathered from, and left. It was a monument to what human beings could do, and it was also a dead end. You could not stay, you could not build, you could not refuel and press on. You went because it was hard, and you came home because there was nothing there to hold you. The moon of the neutron map is a different world. It is not the end of a road. It is a place along the way. It is where ships will pause to fill their tanks before the long crossing to Mars. It is where the first permanent home beyond the Earth will most likely be built, out of water drawn from the shadows and soil piled from the sunlit ridges above them. It is, perhaps, where a child will one day be born who looks up at a small blue-green Earth in a black sky and understands, without having to be told, that home is not one world but several. None of that is close. The difficulties are real and stubborn, the dust that destroys machines, the cold that cracks metal, the radiation that has to be hidden from, the sheer loneliness of a few people in a small shelter on a barren world. No one has yet pulled a single litre of water from the lunar ground. The law that would govern the mining does not exist. The economics look sound only on paper. There will be more failures, more landers that crash, more machines that freeze, more plans that slip. The South Pole will not be settled quickly, and it will not be settled cleanly. But none of that touches what the map shows. The water is there. It is not a theory and not a hope. It is a measured quantity, charted finely enough to guide a lander to within a few hundred meters of the richest ground. The speculation has become a certainty. The question is no longer whether human beings can live on the moon. It is only how, and when, and who. Someday, the neutron detector will fall silent. The rare helium in its tubes will run low, or its electronics will fail, or its orbit will decay and carry it down into the surface it spent so long studying. When that day comes, it will have worked far longer than anyone dared to design for, and it will leave behind a record spanning more than a full cycle of the sun's activity, not just a snapshot of where the hydrogen sits, but a long, slow film of how the volatiles at the pole shift and breathe over the years. That record will be studied for decades after the instrument itself goes quiet. The lander that was meant to reach down and touch the ice is gone. But what it was reaching for is not gone. It is in every study of where the next cruise will land, in every plan for a machine to melt water from the soil, in the shared understanding, now held by every nation that reaches for space, that this small, cold, shadowed region at the bottom of the moon is the most valuable ground off the Earth. It is in the quiet shift from if to how that has changed the entire conversation about leaving our planet. And when the first permanent base does rise at the South Pole, when the first water is finally dug and split and burned to send a ship onward to Mars, the people who do that work will be standing on a foundation laid by a map made by physicists in Moscow who spent decades solving a problem that sounded, at the time, almost absurd in its specificity. How do you focus neutrons, which cannot be focused, onto a patch of frozen ground a few kilometers wide, from an orbit 50 kilometers up, in order to count atoms of hydrogen buried under a meter of rock, in a darkness the sun has not entered in 2 billion years? They solved it. They built the instrument. They delivered the map. And then, the map became the future. The moon is a port now. The harbor is charted. The ice is waiting in the dark. Good night.